should be recording. And so now we're going to do example 4. Let's take a look at the example. We've just completed example 3, and by the time you're watching this video, again, there'll be links here to the video. So this will be our first example containing a network that has a loop structure in it. So this is fairly representative of practical networks. A very simple one. Simple in the sense it's not complex, but it's very much relevant. It has almost all the hydraulic pieces that you would encounter in any real network simulation. And we're challenged with water supply network shown below. Has a constant head elevation storage tank at A. This one is at 75 meter pool elevation, and this one is at 70 meter pool elevation.
Yeah.
And it's got these nodes A, B, C, and D. We're told the entire network is on flat terrain. That's kind of a suspicious statement, but we'll go with it. And at node B, there is 0.2 of a cubic meter per second forced into the network. How that is done is not told to us explicitly in this problem statement. So we're going to model that as a negative demand. At location D, we have 0.2 cubic meters per second taken out of the network. That's an ordinary demand under the usual conditions. We're given the pipe lengths and diameters. So A to D is 1,000 meter long, 400 millimeter diameter. Length A to B, 700 meters long, 250 millimeter diameter. Length BC, 800 meters long, 300 millimeter diameter. And length DC, 1,200 meters long, 350 millimeter diameter. Later on it says if the node elevations are 50 meters. Oh, okay. Yeah, flat terrain just means that there's no difference in elevation between A and B. It doesn't mean it's at 0. And in this case, we're told that everything is set at 50 meters. All the pipes are ductile iron. So we want to determine what the inflow or outflow from the storage tanks would be. So an interesting question. We know 0.2 coming in here, leaving here, the flows are going to balance. But this storage tank has 5 more meters than this one. We want to know how the water is going to leave this 75 meter tank and enter the 70 meter tank. So when doing that, if we're using the interface, we would follow the same protocol as we've been doing, or at least implicitly. I didn't explicitly state these. We get the image into a bitmap so we can draw things. Start EPANET, set defaults, import background. Put the reservoirs on, put the nodes on, put the links on, set the total heads, set the pipe length and diameter, save the input file, run the program, and check if I have looks like I have a video of this one already going on. So we'll just have a second video since I'm recording right now. So let's go ahead and get the EPANET running. Or we're going to have our network challenges again all of a sudden. Looks like we might. Looks like I got kicked off the internet. That's weird. Well, that's the consequence of working in 3 or 4 different networks at once. Okay, so we'll go ahead and let's get the software loaded.
Okay.
So we'll import, load in the base map, and this one's already there. It's under example 4. And does that look like the picture in the notes? It surely does. And since we're going to the trouble of making the video, let's go ahead and do the problem under the full formality method. Just invented that word. Okay, so there's the map. So the first thing we have to do is lay out nodes or reservoirs. Doesn't really matter which. I'll do the 2 reservoirs, then we'll put in the nodes and proceed accordingly. So we'll have one reservoir, then the other reservoir, then we choose the nodes, which is this button, A, B, C, D. We can conceivably go label things. What do you want to call this one? Reservoir 1. And that one is at 75 meters. Although the program doesn't know the elevations yet. This one we'll call R2. That's at 70 meters. So the reservoirs are established. Actually, let me modify the appearance slightly. The aesthetics of what you draw is kind of up to you. Now we were told that all the junctions are at 50 feet. What's the easiest way to change them all to 50? Using the group edit tool. Edit, group edit, junctions, elevation, 50, press the OK. OK. We're done. So they're now all at 50 feet. Now, we've got to remember we're not completed yet because we still don't have any of the pipes. We'll load in the backdrop to help us draw the network. So we need that pipe, that pipe, that pipe, that pipe. So those pipes are drawn. There's 2 that I don't have drawn yet. I don't have this one or this one. I'll get those in a second. Let's go ahead and start parameterizing these pipes. This is a 700 by 250. So we tell it 700 units long, 250 millimeters in diameter, and if we use Darcy-Weisbach, I think we'll use 0.1 for roughness height for ductile iron. This one is 800 by 300, roughness 0.1. This one's 1200 by 350. 1200, 350, 0.1. Last one, 1400, 0.1. Okay, the interior pipes are basically defined. Let's go ahead and deal with these demands. So junction 4 has a minus 0.2. The minus sign is indicating that we're putting water into the network at this location. At this one, we're going to have, we got to get the right object. We're going to have a positive demand, so that 0.2 is coming out of the network. And let's go ahead and get them in the correct units. The program does not do meters cubed per second. Closest is liters per second. So this is actually going to be 200 liters per second. I'm lucky I just noticed that. Alright, so now those are all taken care of. The last thing we have to do is these short pipes that connect to the reservoir, or connect to the various reservoirs. So I'll let you help me with that. These pipes, we don't want them to be very long, but we do want them to have big diameters. And we'll keep our roughness. Okay, so it's very short pipe, basically 10 meters long, a meter in diameter. So it's as if that reservoir is directly connected to that point. There's no head loss in that section of pipe. We'll do the same here. Now, in a real analysis, if you actually know the dimensions of the connection, by all means use them. Okay, our model is almost set up. We have one last thing to take care of, is to get the units set correctly. We're going to use liters per second, and we'll use the Darcy-Weisbach head loss equation because that's what I entered data for. Choose OK, and now we're ready to try to run it. Yeah. So to run it, claims the run was successful. That's always a happy outcome. Let's go ahead and turn on the flows. In the nodes, we'll put, I think we want pressures. We actually want to see the numbers. And albeit the actual figures are a little small, but we'll compare that to what's in the notation. It's saying that And this one is 190, almost 200 liters per second in pipe 3, and let's see what it is in the example. We're close. So I will go ahead and we want to save it. We would choose File, Save As.
Exit example 3.
So actually in example 4.
Oh yeah, exit example.
And we're done. So when we're done, we can exit the program and actually disconnect. Again, if you're on your home computer, these steps you wouldn't do because you don't need to disconnect from your computer. And let me stop recording.